right, great. So we have the third lecture of Mukund on AdS CFT. Go ahead.
All right. Thanks, Veronica. All right. So I ended yesterday by trying to fill out this table of the map between boundary conformal operators sitting in representations of the conformal algebra on the boundary of AdS, and fields that are propagating in the bulk. The general rule is simply that the representation content on the both sides must match. So the fields are organized in SOD, 2 irreps, as are gauge invariant single trace operators on the boundary, and one just tries to make an identification based on quantum numbers. Okay, and I'll just say a few words about how the identification is made in abstraction, because I was asked how to generalize from the few examples I gave you. I didn't list out all possible examples. The map between operators to fields is purely kinematic. Because you're just matching quantum numbers on both sides. Masses and spin maps to conformal dimensions and spins. And the relation between delta and M can be determined from just the Gaussian limit. Just we just look at free particles, free fields rather. In AdS p+1. So just look at this free scalar, the free spin massive representation. It will satisfy some wave equation, and as I'll describe to you in this case, the scalar later, that has all the information we need to translate the one relation between the mass and the conformal dimension. The spins go along for the ride because the spin content on both sides is just a statement of what SOD representation we're talking about. And I was also asked the following question afterwards, whether we only restrict ourselves up to spin 2. And the answer is not quite. 2B supergravity or M theory have metric, well, they have gravitons. Maybe it depends on which theory, but in type 2B, we have 2 forms, and let's just say form fields plus fermions. But the form fields are capped in rank. So type 2B only has 2 forms and 4 forms, whereas M theory has a 3 form. So when you do dimensional reduction, sorry, M theory has a 4 form. On internal space, this X we get massless gravitons, gauge fields, scalars, plus massive fields from harmonics. Okay, and so we could study massive spin 2 fields, we could study massive spin 3 halves field, and so on. I'm just not writing out formulas for them. If you want to know what the map is for those guys, then there's a nice table at the end of Doker and Friedman's review from, I guess, by now 2001 TASI lectures. So what I'll try to focus on is deriving the relation for scalars, for just the relation between the dimension and mass for scalars, and show you how to do computations of correlation functions first, and then say a few words about two special cases which have to do with bulk gauge symmetry and bulk diffeomorphisms. Okay. The rest one can work out by just working out, studying the appropriate free field propagators in AdS. So let's try to set up the problem. So let's say for a moment we have this dictionary. We've identified the relation between fields in AdS and operators on the boundary. What should we compute? Well, in the boundary, it's a conformal field theory. So there's a natural set of quantities to compute, which is just some off-shell data of correlation functions. Okay. The bulk theory, however, is gravitational. So there should only be on-shell data in the bulk theory. Just like in the usual way, what we usually do in flat space is we compute S matrices. We compute fix initial conditions and final conditions and do some scattering. So we can imagine doing the same thing here. We can imagine spinning a set of operators on the boundary of AdS spacetime, allowing them to source and create a set of fields that propagate into the bulk, which interact in some fashion and then come out. Okay. So this, I've drawn it very much like a flat space scattering calculation. The main difference is that my asymptotics is not null infinity. I don't have a scri minus to a flat space scri minus and scri plus, but rather I simply have a time like Einstein static universe boundary, and I can put operators at will at different places on that boundary. What I'm going to try to argue is basically to show you how to see this sourcing of how these boundary operators source bulk fields, which then interact through bulk interactions, and translate that calculation into a correlation function calculation in AdS. So this is the standard GKPW dictionary. So indeed, as I said, what we're going to do is we're going to fix asymptotic sources. We're going to see that our fields will have two solutions, one which will be normalizable and one which won't. We'll freeze a non-normalizable part as the source, as the thing that sort of turns on and off an operator in the boundary, and then we'll compute a generating function of correlators as a functional of these sources. Okay, so I've sort of drawn these sources as if the delta function supported at operator insertions, and we'll exactly try to set up that problem in that. So I'll use the following notation. I'll use J to denote an arbitrary correction of boundary sources, and I'll try to compute the following quantity, the generating function of correlation functions as a functional of these boundary sources, which I'll just write as the following CFT object. It's basically trying to add a local source corresponding to the appropriate operator, and then trying to do the functional integral over all the CFT fields. Okay, let me use the word X for CFT, so I'll use phi for bulk fields. And I want to say that this is the same as computing the bulk path integral of with the boundary value of fields set to be j. Okay, and I'm cheating here. I'm saying, we're going to use the string action, but really we aren't. We are going to sort of truncate this to supergravity action in what follows. Okay, so maybe I will use the word gravity here to indicate that I'm just going to use the bulk gravitational picture. It could have been string theory if you're actually trying to compute correlators exact to some orders in alpha prime. For the rest of today, I'm going to make a simplification. I'm not going to talk about Lorentz and AdS. Okay, there's a reason for it. We could do the calculation in global AdS. There isn't a problem, by and large, apart from one of having to describe time ordering to tell me which correlator I'm computing. There's a minor technical problem which will be important later, which is that in Lorentz signature, there exist solutions that are purely normalizable. You don't have to turn on non-normalizable sources. So one has to deal with them, and I'm going to try to put that aside for the moment and not deal with them. And so I'm just going to try to do the computation for the Euclidean correlators by working in Euclidean AdS, and this will turn out to be a very straightforward boundary value problem. Okay, so it will save me the trouble of the question that I was asked yesterday, that in global AdS, the spacetime is not globally hyperbolic, so I have to specify boundary initial value problem, and I'm going to elide over that for a second by not working with hyperbolic equations at all, but just with elliptic equations of a Euclidean spacetime. So I'll draw the following cartoon, which is basically the Euclidean AdS cartoon. So think of this as a Poincare disk, and now the scattering problem is specifying boundary insertions on the edge of this disk, and the fields propagate, quote unquote. This is Euclidean, so nothing really propagates, but we will talk of propagation in the radial direction. So the radial direction goes in, z is my radial coordinate, and z is 0 is a boundary in this Euclidean AdS, which I'm using in these Poincare coordinates. And then there's some interaction. The nature of the interaction depends on what bulk theory I consider. For starters, I'm actually going to switch off the bulk interactions. I'm just going to study the bulk Gaussian theory to motivate to you just computing the basic correlators, just 2-point functions, okay, which we can do without worrying about how the bulk fields interact. And then I can turn on the interactions and study them term by term in perturbation theory. So since I'm only talking about scalar fields, I'll have a single scalar field phi with some mass m, and I've written down the Euclidean action for it in AdS. For now, gravity is a spectator. So the only place where the fact that I'm in AdS enters is in the fact that I have the Klein-Gordon action in the gravitational background. So I will have to specify at some point some boundary conditions, because this is really a space-time with a finite boundary, and I will have to specify some regulating terms to compute physical finite correlation functions, which I will call the counter term action. Okay. Now, in the literature, these things are often written down together as a single boundary term, which is true. They're both terms that don't. Oops, there's a typo here. This is d plus 1. This is a bulk action. These are both integrals over the boundary of AdS of the boundary value. They are functionals of the boundary value of the field. And as a useful mnemonic, I'm also cheating. There's no root. I'm Euclidean, so there's no minus root g. This is just, and I'll use gamma as the boundary metric. Okay. So my boundary metric is going to be gamma, which is the metric induced on the hypersurface z equals 0 from the bulk. In this case, it's just the limit. It's just going to be the flat metric on RD, or if I conformally compactify the metric on SD. For purpose of, as you take the limit, you see that this z squared blows up because z is going to 0. So we'll often try to do these computations by regulating at some small radius, z equals epsilon, and then taking the limit epsilon goes to 0 afterwards. Okay, so we'll put in a finite cutoff and do calculations with the rigid cutoff. Okay, so with that preamble, let me now start talking about solutions and see what we get. And I'll tell you a couple of different ways of doing these calculations, that some of which are quite straightforward and some involve using some tricks. Let me say at the outset that whatever correlators I compute in the Euclidean domain, they will give me appropriately correlators in the space-like domain of the Lorentz signature geometry. Okay, because I can just analytically continue the time and as long as I keep the insertion points suitably spaced like to each other. It's just that these are conformal correlators, so they have branch cuts on the light cone. So continuing past the light cone is the tricky part in taking these correlators and getting the real-time correlators, because that needs a regulator, that needs an appropriate I epsilon prescription to tell you which correlator you're computing. But that can be done. So at least since all I'm going to compute for a while is the correlators in the vacuum, then those are pretty straightforward things to do. So there is no, in some sense, there is no loss of information in just doing the Euclidean correlators. So let's look at the equation of motion from the scalar field action. Just the standard Klein-Gordon equation, which I've written out here. So I'll call that E5. And AdS is a nice enough space-time that you can solve this equation exactly. But let me write down the solution. I'll write the solution by working in RD, Fourier, decomposing it into Fourier modes along the spatial boundary directions. And I claim the solution is given by a Bessel function. And of course, p squared is positive because this is, we're in the space-like domain. Okay, so you can write down the wave equation and just check that the solution is a Bessel equation, and the solution is given by this. And this solution, okay, I also said that the way I'm going to interpret this problem is I'm going to think about evolving radially inward from the boundary. And so I can try to do a classical analysis of the momentum conjugate to this radial evolution direction. So I'll define the conjugate momentum to the field with the conjugate momentum density with appropriate root g's as the derivative in the radial direction. Okay. And then you can just compute the variation of the action. You'll get the usual piece, which is the equation of motion times the variation of the field. And then you'll get another piece, which is coming from integration by parts. When you derive the equation of motion, you have to integrate this first term by parts, and that term will give you one boundary term proportional to pi phi. Okay. Now, for the scalar field, if I want to get the correct variational principle, then I get the equation of motion as long as I freeze phi on the boundary. Okay. So I'm just going to impose the Dirichlet boundary conditions. For the boundary of AdS. Okay, so that fixes in, and in fact, I need no boundary term here because the Dirichlet boundary conditions are automatically satisfied by setting delta phi, holding delta phi fixed on the boundary.
Excuse me, can I ask you a question?
Certainly.
Can you please say again why delta equals delta plus corresponds to the Dirichlet boundary condition?
I'm just holding the field value fixed on the boundary. To get the equation of motion, I need the coefficient of, I need to kill this term. I need to kill the boundary term. So the two ways to do it. One is to basically say, and the only thing, if I have this action, the only boundary term I get is the term proportional to delta phi, pi phi times delta phi. So as long as I hold delta phi on the boundary fixed, then I can drop this term and there is no boundary contribution from here. So variational principle is satisfied.
Now, I understand that the only thing I don't understand is why the scaling dimension being delta plus implies that that's like the relationship between the fact that the scaling dimension of the operator in the CFT is equal to delta plus is related to the Dirichlet boundary condition.
Good. I haven't explained that, so I'm coming there.
Okay, sorry. Because I saw it in the box above, I thought I missed it.
Yes. I've just put it there, but I didn't say where that's coming from. So now I try to look at what the solution looks like. So now I'll explain where that comes from. Now let's look at how this behaves at infinity. Okay, so, sorry, at the boundary, z equals 0. And the Bessel function has two fall-offs. So we can look at the solution near the boundary. The other way. And I find that I have two fall-offs, one which is delta plus and one which is delta minus. Delta minus is a slower fall-off, and delta plus and minus are basically determined from the asymptotics in terms of the space-time dimension and the mass of the field. Okay. And I now need to ask, which part of the field do I need to freeze? Now, this is where the Euclidean problem is much nicer, because you see the Euclidean geometry is basically a ball. It's topologically a ball. So the solution needs to be regular everywhere inside the ball. Okay. If you want regularity of the solution everywhere inside the ball, then you find that you don't, so that takes care of one boundary condition. This is a second order differential equation. And so I want my solution to behave smoothly at the origin. That tells me that I have no choice but at infinity to have the slow fall off mode a times z to the delta minus. Okay. which means that the value of the field has to be fixed by freezing A and letting B be determined by the smoothness condition at the origin. So this mode, the coefficient A is usually with the coefficient of zeta delta minus, is called a non-normalizable mode because it's not normalizable with respect to the Klein-Gordon norm. This mode is normal. So, and I really am using a description that is slightly more adapted to the Lorentzian signature, because this mode in Lorentz signature will be truly normalizable. However, in the Euclidean problem, because this is elliptic, I only get to fix boundary conditions. And the only boundary condition I'm allowed to fix is the leading fall off. So subleading fall off gets determined by smoothness. So all problems you want to solve in Euclidean AdS are nice because you just fix the field value at infinity as if this was like a conductor, and then the interior field values are completely determined. So it's basically like doing electrostatics. In fact, you'll see in a moment that there's actually quite a formal analogy with electrostatics in terms of Poisson kernels. And that's why the boundary condition is Dirichlet. But if we go back to our metric, you see that this metric enjoys scale invariance. Under z to lambda z and x to lambda x, the scale invariance. But the scaling is really dilatation from the point of view of the boundary, because it's just scaling up the boundary coordinates. So if I have a solution where I have a mode that scales like delta minus, and I'm going to have to integrate this against a source, then it immediately follows that the dimension, well, it also helps to note immediately that delta minus plus delta plus is D. So freezing this mode means that the corresponding operator dimension is the coefficient of delta plus, and therefore it's delta plus by scaling. So that's where the dimensions come from. The dimensions come from just thinking about how we're adding this term in the action, because this term is added with a d-dimensional integral. And if O has scaling dimension delta, then J has scaling dimension d minus delta. So going back to Stefano's question, the statement really is the Dirichlet boundary condition here is picking out for us the freezing of this slow fall off mode, and therefore saying that the conformal dimension is delta plus. I won't go through the exercise, but I pointed out to you there are special cases in my table that if I use the delta plus boundary condition, then I don't attain the unitarity bound. To go below this d over 2 bound and attain the unit and get to closer to the unitarity bound, I have to impose an alternate boundary condition, which, if you see my formula now, is basically requiring my field to have operator to have dimension delta minus. That means switching between freezing A to freezing B. You can do it provided it just so happens that both modes, delta plus and delta minus, happen to be normalizable with respect to a suitable norm, which is not the Klein-Gordon norm, but a deformed Klein-Gordon norm. But that can only be done for some range of masses, not for all range of masses. But like with any classical problem, freezing this guy instead of freezing this guy can be achieved by doing a Legendre transformation. Okay, because if I basically add a term to the boundary action, which is pi phi times phi, then I'll get an additional boundary variation which will cancel this term and leave behind delta pi phi phi. So freezing delta pi phi to 0 is the Neumann boundary condition, because Neumann boundary condition basically says fixed normal derivatives. So to obtain the alternate quantization, we need to do this. Okay, so I won't sort of belabor the point, but in a smaller range of masses, one is allowed to use Neumann boundary conditions, but then the conformal dimension of the operator is different. It's not delta plus, it's delta minus. For the sake of simplicity, I will only do the computation with the Dirichlet boundary conditions. And so I'm restricting myself to talk about operators with dimension bigger than d over 2. Okay. There's some funny things about operators with Neumann boundary conditions. Realize that the bound here is a d over 2. The switching off between them is at bounded at d over 2. So whenever you impose, so if phi has dimension bigger than d over 2, it means phi squared has dimension bigger than d. So it's an irrelevant operator. But if phi has dimension between d over 2 minus 1 and d over 2, then its powers can be relevant. In fact, its second power is definitely relevant. So the range of Neumann boundary conditions is exactly the place where multi-traces become relevant operators, okay, from a conformal field theory point of view. Let me pause here to make sure people are happy with this discussion. If you need more elaboration, I can supply more intuition for why we are doing this quantization this way. Okay, so now once we have figured out what boundary condition to impose and how to identify the field with the corresponding operator on the boundary, we can now go ahead and try to compute the correlators. So what I'm going to do is I'm going to freeze source, in this case, J of P on the boundary. Sorry, not freeze. So I prescribe some source in momentum space, and I write the solution with a cutoff. Don't need to worry about these various prefactors. So phi at epsilon p is basically J. Sorry, this is getting a bit messy for my taste. Very good. And now I can, what can I compute? Well, if I go back to my action, I can try to compute the on-shell action with the source value prescribed. There's no boundary term to evaluate. We'll worry about the counter terms in a second. But I've prescribed some boundary values. The action is a functional of those boundary values. But I don't have to do any bulk integral because on shell, I can use equations of motion and integrate by parts. So I only have to calculate phi times pi phi, no deltas anymore. And they are quadratic in the sources. So we can compute this, and I claim, and if I vary that with respect to, so we compute S on shell. This is some functional of J. In fact, it's quadratic in J. And if I vary this S on shell with respect to J, this will give me the 2-point function of the corresponding operator. In fact, if I don't vary, I just get the generating function of correlators to whatever order I'm working in. But since I'm doing a Gaussian theory, the generating function is easy to compute. If I was doing some higher order theory, I'd have to actually do the integrals. So now we can just calculate this 2-point function by evaluating the on-shell action and basically dividing out by J because you just differentiate twice. And essentially all the terms are coming from the boundary values of the Bessel function, and you get a simple power law up to some ratio of gamma functions. These gamma functions are coming from asymptotics of Bessel. But going back to Fourier transforming back to position space, this tells you the position space correlator, which is exactly what you expect for a conformal correlator. Okay, this delta is delta plus. Okay, so sorry, I already said that in my box, so I'll just keep it at delta. So this is the most straightforward way to do the calculation. You fix boundary conditions at some cutoff and just evaluate the 2-point function by computing the on-shell value. And for those of you who are asking, where do I get this relation from for other fields, you repeat the exercise for other fields. Just look at asymptotic falloffs, see what mode you have to keep fixed, and whatever mode you have to keep fixed, which is like this delta analog of z to the delta minus, immediately tells you how to fill out the rest of my table. In fact, you don't have to solve the wave equation, you just have to look at the asymptotic falloffs of the solutions to get the table filled out this way. There's another way to do the calculation, which is equivalent, but some nicer for doing higher point functions, which is to view this calculation as propagating a field from a source on the boundary into the bulk, as I was describing before. So imagine you turn on J here, and then you ask, how does it source the corresponding field into the bulk? So that we can do by writing an appropriate Green's function solution, or in the language of electromagnetism, a standard Poisson kernel formula. So remember, Poisson kernels are written for solving electrostatics problems for finite domains in 2-dimensional electrostatics, because the Poisson kernel comes out naturally from Cauchy integral formula. So you can just write down an appropriate propagator that propagates you from a boundary point into the bulk, which I'll call K delta. And I'll normalize it by demanding that as I go to the boundary, after stripping off the power of z to the delta minus, this K delta is 1. This power is just z to the delta minus. And in fact, that's how the calculation was first done in Witten's paper, because he just wrote down the position space bulk to boundary propagator by using conformal transformation properties of the conformal properties of the AdS spacetime, and the bulk to boundary propagator to propagate from boundary point 0y to bulk point zx is simply given by this Poisson kernel, hyperbolic Poisson kernel. And if you have this, you could just now take this and take the limit z goes to 0, and you'll see that this really gives you x minus y to the power 2 delta, which is exactly the limit as you are. If you sort of don't propagate, you'll get the conformal correlator correctly. When you're doing calculations with a fixed cutoff, I cheated in writing this formula. There are subleading divergences here, the terms that blow up as epsilon goes to 0, and they need to be regulated. You can regulate them by adding a counter term action, which is the whole story of holographic renormalization. The counter terms you can add are the same kind of counter terms you can add in field theory. They're local functionals of the boundary fields and their derivatives. So if I have a boundary metric gamma, I can add counter terms that are quadratic in the boundary values of the fields up to derivative corrections, and you can work out, depending on what the dimension is and what of the operator and what space-time dimension you're in, how to cancel divergences order by order in boundary derivatives. So this delta gamma is like factor of p squared. And I'm just organized it order by order in powers of momentum. And there's a nice organizational principle that you can sort of systematically try to compute these coefficients, which are all that you need to know how to get finite answers.
Hi, just a question. Do these coefficients depend on the specific regulator that you used to get rid of the divergence, or are they universal?
There is some scheme dependence because these are just regulators. The finite answer is what is universal here. And I have chosen to use a regulator that basically follows by cutting things off nicely. Okay. Now, the way I've written it, the way I like to do it is to write it in terms of a boundary action, which has one advantage, that now it's completely covariant with respect to bulk choice of radial coordinates. So you can use this action to compute it in any coordinate frame you like. There are schemes where people like to write this in particular radial gauge choices, with trying to write coefficients in a particular grade expansion with respect to.
But isn't then the choice of this? Oh, but this boundary is the actual boundary, not the z equals epsilon boundary.
Correct.
Oh, okay.
Yeah, this is the actual boundary. So I'm actually imagining that I've stripped off powers and written it that way. So if you evaluate things, you will evaluate them by putting on epsilon regulator and find that the divergent terms and powers of epsilon will cancel between this term and the terms that come from the bulk.
Oh, okay.
So I like to write this because then it's as if I'm writing a regulator action in the field theory without telling you where I'm putting cutoffs and whether my cutoff is homogeneous along the boundary or whether my cutoff is inhomogeneous along the boundary. So that's all subsumed in this integral.
Okay, thank you.
Can I ask a question?
Yeah.
You said something about taking z to 0 in the first equation here. Could you repeat what that is interpreted as? I'm
saying that if you think of what the bulk to boundary there were two I sort of spoke too fast. If you take z to 0 here, this Poisson kernel becomes a delta function. So basically it's a propagator propagating from this point in. So on the boundary is the source. It's a solution. It's a solution to the inhomogeneous equation with a source on the boundary at the position y. So you should get a delta function of x minus y. But I'm saying the powers here are such that if you take the limit and strip off the appropriate power of z, then you should get back the 2-point function of an operator of dimension delta.
But I mean, geometrically, is this some kind of a boundary to boundary propagation?
It's a boundary to bulk propagation. So it's a propagation. Yes. Sorry. Sorry. Yes. What you asked is indeed a boundary to boundary propagation. So indeed.
So does it go through the bulk or does it go along the boundary?
It goes through the bulk.
Okay.
But it's really reduces to stuff that goes along the. It's on shell through the bulk, so you can pull it back to the boundary.
Okay.
So in pictures, it's a bit like this. So this is the propagator. This evaluates for me the field value here, given source here, or given unit source here, right? So that's what K does. With the unit source, it propagates me to phi at some point in the bulk. Now I'm saying take this endpoint and push it all the way here. Then this should give me a boundary to boundary 2-point function, provided I suitably strip off powers of z. Okay. So I'm just saying that there's a nice way to get the boundary 2-point function by taking the bulk, some limit as z goes to 0 of k delta with some z power stripped off. If I push this endpoint here, I'll get delta function. But if I push the endpoint anywhere else, if it's not coincident point, then I get the propagator. Then I get the correlate.
Sorry. You said you can pull it back to the boundary. Is there a major arc, minor arc ambiguity, or is it always the minor arc? How do you pull it back to the boundary?
No, I meant something very simple-minded. When I said pull it back to the boundary, I'm saying if you propagate epsilon distance and come back, if you don't propagate, if you just here. Yeah.
Oh, okay.
Yeah.
Okay, thank you.
I'll say more about these counter terms when I come to gravity, and for scalars, it's a matter of just looking at the Bessel functions and evaluating the terms, and organizing them in powers of momentum. Okay, so it's pretty straightforward for scalars, and this is well discussed. This is well discussed in the Doker-Friedman review, for example, and also in Skenderis's lectures on holographic renormalization. This bulk to boundary propagator is very useful if you want to start computing higher point functions. So now let's add in a bulk interaction. So let's put S phi to have a term like lambda phi cubed. Okay. So let's say there's a 3-point vertex in the bulk. The propagator structure is still what I computed because it's just propagating the field with respect to the free theory. And I want to compute the boundary 3-point function at order lambda. Or maybe let me not use lambda, since I use lambda for the 't Hooft coupling, let's use G. Can't use G either, H. So the 3-point function at leading order in H comes from this diagram. Because phi has a vertex in the bulk, which is of order H. And I can get to that vertex by propagating 3 different fields and making them meet. Okay. Or you can do the following. you can go back to my action with the phi cube term. So here you can imagine having an h phi cube term, and you can plug in the solution obtained at quadratic order for the quadratic action. These two terms will go away. And in perturbation theory, to leading order, the h phi cube term will have this phi evaluated on the solution to the Gaussian theory. Standard perturbation theory will tell you that and you can reorganize that in terms of thinking about propagating the field from 3 different points on the boundary to come and meet at this vertex. Or we can think about it slightly differently. We can think about putting an operator here, an operator here, and an operator here. These are sources for the bulk field. The bulk field being sourced there propagates inward and gets to meet its other pieces from the phi cube vertex at this point. But I have to integrate over this point. Because in the action, this h cube term comes inside the integral. So what you're left with is taking 3 gadgets of this kind, let's say computing in position space, and convolving them with 3 different boundary points, y1, y2, and y3. This should compute for us, I claim, the 3-point function of 3 conformal primary operators we mentioned delta. Okay, and this is what Witten argued for, and that gives you the standard 3-point Witten diagram as a tree-level Feynman diagram of classical fields in AdS. The integral was first computed by the MIT group using a very clever trick. One knows the structure of a 3-point function of conformal primaries is given by a product of power laws. And they use the conformal inversion trick. They use the fact that these are sort of these functions, these propagators have nice transformation properties under conformal symmetry. They use the conformal inversion trick to pull out the leading boundary powers and then do the integral by Feynman parameters. Okay. So this calculation can be done. And in principle, one can compute higher point functions the same way at various orders. Now, let's say our bulk theory was phi cube theory. Then I would have 4-point functions coming from exchanges. I could, in addition, have 4-point contact vertices. So I could have mixture of exchanges and contacts when I'm computing 4-point functions, and so on and so forth. The contact diagram was also evaluated in the old days, and it's given by some special class of conformal integrals. This exchange diagram involves one new ingredient, because here, between these 2 vertices, we have a bulk-to-bulk propagator. So you have to compute the bulk-to-bulk propagator, but once you know the bulk-to-boundary propagator, you can get the bulk-to-bulk propagator by standard method of variation, some Wronskian trick. Anyway, this is in AdS spacetime, so this spacetime is nice and symmetric. So these bulk-to propagators were computed for various fields of various spin in the early days of AdS CFT. So you can find those in the literature. But even if you have the bulk-to-bulk propagators, you have to do this double integral in the bulk. And this turned out to be pretty formidable. There are a couple of tricks people used. I'll just point out for now that this calculation was finally done for supergravity fields a couple of years ago by Rastelli and Zhao, not by doing direct integrals, but by using some very clever tricks in Mellin space. So 4-point functions are known. They're known in closed form for supergravity fields, but they were easiest to do by exploiting some tricks. Okay, questions about the general structure of computing correlation functions?
This may be a bit naive, but do you only get tree diagrams like this, or does it become similar to field theory that in principle, if these integrals weren't impossibly hard, you'd get also loops in the bulk?
We would certainly get loops in the bulk, so let's try to see what the loops would mean. So if we have a bulk loop, let's say in this 4-point function, this loop would have supergravity field, would have all the bulk fields. And these are down in 1/n, they're non-planar graphs.
Ah, of course, because 1/n corrections become quantum corrections.
Exactly. Right.
Oh, okay. So when you start getting quantum corrections, it's non-planar. Okay.
That's right. So these loop corrections, bulk loop corrections are non-planar corrections. They have been computed for some examples. But it's not systematically explored.
Thank you.
Do you also get counter terms for the cubic and higher order interactions?
No. Well, it depends how you compute them. So my understanding is no. If you compute these cubic diagrams not in position, so the calculations that are typically done are done in position space, because this integral is easy to do in position space. If you try to do them with in momentum space, which is a slightly odd thing to do for conformal field theories, because momentum representations are not nice, because they have cuts. They have these kind of cuts. You can try to, the integrals are actually much more, somehow a bit more straightforward. They have been analyzed, but I don't think you get additional counter terms. But let me take a rain check on that. So this the structure of momentum space integrals coming from convolving bulk to boundary propagators is very well discussed in series of papers by Bozowski, McFadden, and Skenderis from circa 5 years ago or 6 years ago. But let me double check on the counter terms. My understanding is you shouldn't have to add any.
I have a question.
Yeah.
I'm a bit confused about how the loop diagrams arise from the GKPW dictionary. I understand how the tree level diagrams come about.
Yeah.
Just from the relationship between the CFT generating functional and the path integral in the bulk with the gravitational action. But I don't see how a loop diagram would arise.
Well, I mean, one reason to think of why the loop diagram would arise is that in the bulk, you'd have to promote the fields to, suppose you're doing standard quantization of these fields in the bulk. When you're doing tree level, you're treating these fields as classical fields. But once you are doing quantum dynamics in the bulk, you have to allow these fields to run in loops. So the GKPW dictionary, if I go back here to my statement, I truncated these to tree level gravity, but I didn't have to. This is really a quantum integral. This is a path integral over all bulk fields. Potentially, it's a path integral over the full string fields. Okay. In the classical limit too, even if we truncate even if we throw away all the stringy modes, what we have left is the integral over supergravity modes. But then you have to path integrate over the supergravity modes, which means you have to allow them to run in loops. It's just that maybe the better way to think about answering your question is as follows. Imagine evaluating this path integral in saddle point. The GKPW dictionary classically will give you the tree level answers, the tree level saddle values, which you can just evaluate the integral, and then on shell actions give you these solutions. But then you have to compute determinants around them. Those determinants would involve the loops. Does it make sense?
I have to think about it, but I can come back.
Yeah. And indeed, that's maybe a better way to answer the earlier question. That's where the factor of 1 over n is hidden, because this gravitational action is multiplied by 1 over is multiplied by C effective. So I should put that here already.
Yeah, yes, that makes a lot of sense. Thank you.
Sorry, I have a question.
Sure.
So for the 4-point function, is there some CFT interpretation for each diagram you have? Like,
yeah. So I wasn't going to talk in detail about this because I'm sure Eric Perlmutter will talk about this in his lectures. So the CFT OP is in these diagrams.
Mm-hmm.
Okay. So you can look at the OPE of four external operators, and to leading order in the large N, this should satisfy bootstrap constraints.
Uh-huh.
Okay. So you'll have exchanges. I have drawn one particular channel of exchange. There can be other exchange channels. I have sum over all exchanges, and then the contact. There's something nice about the large N theories, that this contact comes from that you can, and which is what is exploited in this Mellin representation, that the exchanges, the only things that are exchanged are double trace operators.
Uh-huh.
Okay. So there's some very nice structure which makes the evaluation easy, because you can evaluate contacts and then you can sort of put the exchanges in a nice fashion. Let me say one thing which is quite nice. So the Mellin representation of the correlator is an integral transform of the standard position space correlator with respect to some integration variable, some variable, just like the conformal dimension. In that representation, this 4-point function with the exchange can be truncated to a contact of the following kind. Some star-like diagram. Because you can act with a bulk equation of motion and convert this to a delta function and push it to the boundary. Okay. So, but this is very important in understanding some of the recent bootstrap stuff in AdS CFT. Large N bootstrap, analytic bootstrap results are sort of crucially contained in here.
Thanks.
Any other questions, folks? All right, so that's all I want to say for now about computing correlation functions. Let me say in the last 10 odd minutes, a few words about two other class of fields, which will be important in our subsequent discussion. The first, I'll talk about bulk gauge fields. So I'll take a bulk field which satisfies Maxwell's equation. So So bulk action. So you can, this field will come from Kaluza-Klein reduction, some harmonic on the internal space. And if you look at Maxwell's equations in AdS and look at the asymptotics, you'll find that there's one piece which goes like a constant and one piece that goes like z to the d minus 3. This is a linear, just Maxwell's equations, and I'm working in radial gauge. Is equals 0. This power immediately tells you what the conformal dimension of the operator is. So now, sorry, I apologize for my leaning on notation heavily. JMU will refer to currents. J is not a source. Now it's the operator. It's a current operator. I'm raising an index, so I get 2 extra powers, and its dimension is d minus 1. Just remember that for tensor operators, conformal dimension cares about where you put indices because of the fact that under scaling, metric has weight 2. The radial, but this is a Maxwell theory, so there's a radial Gauss constraint. So if you're thinking of evolution along the radial direction, then the Gauss constraint needs to be respected, and that Gauss constraint precisely says that this current is conserved. In fact, this current is conserved slice by slice. So if you think of the boundary at z equals 0, this conservation holds everywhere on every radial slice, just as it would in the Hamiltonian formulation of Maxwell theory. Because if you impose the Gauss constraint at one time, it stays at all times. In fact, if you write down the Maxwell Hamiltonian, the constraint is explicitly comes in as a Lagrange multiplier. So if you write this term, you'll get, if you write the Hamiltonian for radial decomposition for the Maxwell theory in AdS, you will see that there's a term which is AZ times this constraint. One thing I want to point out is that these are global symmetries from the point of view of the boundary. So they could have anomalies, they could have 't Hooft anomalies. And that would typically mean that these global currents, they're not conserved if you turn on boundary sources. So if I turn on a non-zero A mu on the boundary, my current will no longer be conserved, but it will fail to be conserved by some functional of A mu. Okay, so remind you that in 4 dimensions, it will tell me that the current conservation is violated by a term proportional to E dot B. So standard chiral anomaly, the ABJ anomaly. Alternately, if we are trying to compute this generating function for the current correlator as a functional of the boundary value of the gauge potential, that would not transform covariantly under gauge transformations. Because if it did, then it's gauge invariant, but it will have an anomalous gauge transformations. But there's a combination of it and a bulk Chern-Simons term, which transforms covariantly under gauge transformations. This is a standard anomaly inflow picture that some of you might have encountered in quantum field theory. All 't Hooft anomalies can be classified by classifying appropriate Chern-Simons terms. And the anomalous gauge transformation of the quantum field theory generating function is precisely compensated by the boundary term you get by varying the Chern-Simons piece. Now, usually in anomaly inflow, the way you think about it as follows: you think of your quantum field theory on some space, and the Chern-Simons theory as living in a topological space that's 1 dimension higher. And the variation of the Chern-Simons term gives you a bulk current, which I'm calling the Hall current J, which is conserved because the Chern-Simons is topological, and the bulk part of Chern-Simons has no gauge non-invariance. But there's a boundary term from the Chern-Simons variation, which is this Bardeen-Zumino current, which is the same thing that contributes to this delta Z Chern-Simons boundary. I have 5 minutes.
Yes.
And the combination that's covariantly transforms under gauge transformations is a combination of the variation of ZQFT with respect to the boundary gauge potential plus the boundary contribution of the Chern-Simons with respect to the gauge potential. Now, rather remarkably, for consistency, you need such Chern-Simons terms in the bulk because the currents in typical field theories that we encounter can have soft anomalies that we can compute by computing standard, let's say, triangle diagrams in 4 dimensions. And these terms are there in gauge supergravity. And the statement that I want you to take away is that the boundary Thoft anomaly is precisely compensated by bulk Chern-Simons terms. Okay. In fact, the coefficient here of the Chern-Simons term precisely matches the Thoft anomaly that you would compute in perturbative bulk Yang-Mills theory, because the anomalies are one loop exact, so you can't have a different answer at weak coupling and strong coupling. So let me say in the 2 minutes I have the following set of statements about the currents and the gauge potentials. So the gauge fields in AdS 5, let's say, come from 10D metric class 5 form and correspond to KK modes going around the phi sphere, rotating around the phi sphere. Let's say for n equals 4. The theory has an SO6 R symmetry with an anomaly and SO6 gauge supergravity precisely has the corresponding Chern-Simons terms. Good. Let me finish by saying that for the gauge field, we always fix the constant in dimensions AdS 4 and higher, and that gives you current conservation. In AdS 4, you are allowed to fix the current, as I was asked yesterday, and leave free the potential, which means that you don't have a boundary gauge symmetry, but you're gauging the symmetry on the boundary. In AdS 3, you don't have a choice. You have to freeze this term because now it's no longer z to the power. It's a log, and that log grows. And the only choice you have in AdS2, in AdS3 is to is to gauge the boundary current. However, as in most AdS CFT examples with AdS3 bulk, you don't get Maxwell's terms. You only get bulk Chern-Simons theories. So that makes it a bit more palatable. But that's the discussion that perhaps Alex might pick on in his discussion of AdS3 next week. So let me stop there for the day and take questions on this discussion.
Great, thank you. All right, questions for Mukund?
Could you repeat that last statement you were making about for AdS5 and what you can fix and what you can't fix for this gauge field?
Yeah, so we had the gauge potential solution, bulk gauge potential went like constant plus some power law.
Right.
In D greater than or equal to 3, you can fix mu. So Dirichlet boundary conditions. In D equals 3, you can either fix, okay, let me make this more clean. Let me say in D strictly bigger than 3, the only thing you're allowed to do is fix mu. In D equals 3, you can either fix mu or jmu. You're allowed to do both. I can give you an easy piece of intuition of why that's the case. D equals 3 means 4-dimensional AdS. AdS is a conformal manifold. It's conformally flat. Maxwell theory in 4 dimension is conformally is scale invariant. Classically scale invariant. In fact, Maxwell theory is scale invariant. It's a free theory. It's a Gaussian theory. There's no scale. The coupling constant is dimensionless. Fixing mu is like fixing the electric part of the Maxwell field. Fixing jmu is like fixing the magnetic part of the Maxwell field, which is the statement of electric magnetic duality in 4 dimensions, classical electric magnetic duality in 4 dimensions. So in this dimension, this is allowed, and this was first discussed by Witten. There's a very nice discussion of this in a paper by Marolf and Ross on boundary conditions in AdS CFT, vector fields in AdS CFT. The other statement I wanted to make is in D equals 2, only fixing jmu is allowed. You're only allowed to use Neumann boundary conditions. If you're talking about Maxwell fields in AdS3. Because there, the solution, you see this D minus 3 is a threshold. There's a way to understand this D minus 3. If you're in low enough dimensions, the Maxwell solution turns around. It sort of starts growing at long distances, and that's the problem. So you have to freeze the boundary. The growing mode is what you might have wanted to call the current, but you're not allowed to keep it. So you have to integrate over all current values, which means you're gauging the current.
Okay.
The statement I made was that while I discussed Maxwell theories, it just so happens that in most AdS CFT examples with AdS3 bulk, you don't get Maxwell terms. You only get Chern-Simons terms.
Right. Thank you.
Professor, I had a question. I think I've seen in the construction of the BTZ black hole that they use a periodic construction to get the proper space-time. Is that what's going on here when they're fixing JU? Is they're using a lattice construction to fix that current, or?
No. So this current is basically on top. This current is on top of the BTZ construction. So this is like so the BTZ solution, which I'll discuss tomorrow, is a solution where you only have the metric, non-zero, non-trivial metric, no gauge fields. Okay, you could have tried writing a solution for Einstein-Maxwell theory in AdS3, and you will find a solution of Einstein-Maxwell theory where the gauge potential will grow logarithmically as you go towards the boundary. It will have a log z term. And some people like to call this the charged BTZ black hole, like analog of charged Rice-Nordstrom black hole. My statement is that that solution should be interpreted as a charged solution because the charge should be integrated over because the current can't be fixed. The current needs to be integrated over. You have to impose a Gauss law constraint. The only solution you're allowed is the solution where the charge is zero. The net charge is zero.
Thank you. Okay, that makes sense.
Any other questions?
Yeah, I have a question.
Go ahead.
So we computed a 3-point function earlier, but from the large N analysis earlier, we had that the 3-point function scales like subliving in 1 over N, right?
Yeah.
So does that, are we forced to choose like a coupling that scales with the GN or something for the
no, thanks for asking. No. Well, yes and no. So let's do it this way. So if our action has a overall factor of C effective times Gaussian piece, then see the propagators go like 1 over C effective. Maybe the easier way to answer the question is the following. So let's compute this guy. We haven't normalized the 2-point function. So let's compute O1, O2, O3 divided by this is nicely normalized. It doesn't care what normalization I use for the 2-point for the operators. This is proportional to 1 over C effect. Because the way the propagator goes, because the scaling is overall. Same counting as basically on the boundary.
Okay, thank you.
Probably in this case, half. Sorry. Half. At least the way I wrote it is power half. So it's completely consistent with the large N scaling, but that's a bit of a, in some sense, the way the large N works in the bulk is it's just stuck out front in the gravity in 1 over G Newton. Okay. And we'll see this over and over again when we do other things because that factor is important for classical gravitational solutions and so on.
So if I do a field redefinition so that the CF kind of moves into just interaction term, in some sense you could say that the interaction needs a CF.
Well, yes, in the sense that, so if you translate what we are saying into field theory terms, we'll be saying OP coefficients have to be consistent with the large N scaling. And for the factorization to work, it better be the connected part of the correlator to be down in 1 over N. We need appropriately low OPE coefficients.
Yeah, so I can just cook up like a classical field theory result and expect it to kind of be consistent with large N scaling boundary.
Correct.
Great.
You could, so there's a related question, which again, people have explored, but there's no clean answer. So let me tell you the question. I gave you a laundry list of compactifications yesterday, and I said various things about, doing colors applying reduction. And if you really ask where do these interactions come from, they come from the colors applying reduction. And the coefficients are set completely by the size of the internal space. Okay. It's an interesting statement about the examples we know from stringy constructions, that the internal space has a size that's commensurate with the AdS. This is roughly in the AdS 5 cross S5 example, we saw one length scale, LAdS. Both the sphere and the AdS 5 are the same size. In other examples, that's not quite true, but they're not parametrically different. There's no parametric separation of scales. So there's always been this open question, can you have AdS CFT examples where there's a parametric separation of scales between the internal space and the macroscopic AdS size? Could there be an AdS CFT example where you have a tiny internal space of string length? We don't know of a constructive way to get one. People have tried. The best place probably where such a thing might exist is in some flux compactifications. Because flux compactifications naturally give you warped AdS geometry. They give you AdS geometries before you uplift KKLT. And so you might imagine that that gives you interesting examples of AdS CFT correspondence. So people have made interesting attempts to come up with duals for those examples. So there's if I remember correctly, there's a paper from 10, 15 years ago by Polchinski and Silverstein trying to make an argument for some F-theory constructions. But I don't know if there's been a sort of systematic study of such compactifications. Even ask this question, can we get this parametric separation regime? Which will be closer to what you're asking. Can you make OP coefficients at will? Other than, or in field theory parlance, are there non-trivial solutions to bootstrap with funny large N behavior? Don't know.
Great. Thank you.
On a related note, regarding this large N limit, in the field theory way, usually the conclusion is that in the strict planar limit, all the correlators factorize. So only 2-point functions matter. And it is in this strict planar limit that we get classical supergravity. So shouldn't we get that in the strict planar limit, in classical supergravity, interactions don't matter and we only have the disconnected correlators?
Yes, so if you want me to set C effective to infinity, yes. I'm just saying that they order 1 over root C effective.
But then, so if we are starting to compute corrections to the strict planar limit, how are we certain that those corrections come first from that interactions and not from other kinds of quantum corrections?
Good. I think for the 3-point function, it's easier to argue. For the Gaussian theory, if you start with just the Gaussian theory, there's no way to generate a 3-point function without having a contact interaction. Mm-hmm. So that's one. I mean, for 4-point functions, this starts getting tricky because it depends on the leading 3-point interaction. Mm-hmm. But yeah, so there's a disconnected piece, which is nothing happens. But if you remove the disconnected, which is just completely factorized, mm-hmm. But on top of the disconnected piece, there is a leading connected piece. But the system. Maybe the right way to say it is that what one wants to do is at least analyze in all cases the leading 1 over n correction that can be computed from supergravity. Mm-hmm. On top of this, you're of course right that there are loop corrections on top of this. So there is higher order terms which come from bulk loops.
Okay. So as soon as we are considering interactions, so it means we are slightly away from the strict planar limit, and then that's why we also we start getting all the loops and all the diagrams as you would in any QFT.
No, I think there is a I don't think the 1/n connection to the 3-point function, the connected part of the 3-point function is a planar diagram. There are non-planar corrections to 3-point functions which are higher order in the 1/n expansion. It's
Sorry,
just
could you repeat your statement again, please?
Yeah, the leading connected contribution to 3-point function comes from a planar diagram. It's just down in 1/n. It's just the counting is different for correlators than for.
Oh, yes.
Okay, so it's just that so this is indeed, this is coming from the bulk classical theory. It's still planar. There's nothing quantum about it. But then there are subleading quantum corrections coming from loops.
Yes, the counting is different. It's just that, yeah, the connected counting is different for higher point functions. Yes.
Okay.
Thank you.
Can I ask one more question?
Sure.
So could you say maybe something about using, instead of say standard Dirichlet or Neumann boundary conditions, but mixed boundary conditions?
Okay. So indeed, I can. So let's consider the following operator. So let's say we have an operator O of dimension delta. And let's say delta is less than d/2.
Okay.
Then O squared is relevant. So I should be able to deform the theory by adding O squared, and I'll have a non-trivial RG flow.
Right.
So classic example is the Wilson-Fisher theory in 3 dimensions, where the lambda 5 to the 4 interaction is relevant. You can think of, so in fact, we're doing the ON vector model. You can think of phi dot phi squared in Wilson-Fisher is a relevant operator. And this is the matrix analog of that, double trace.
Okay.
If we say that there's a field corresponding to O, then you may ask, what is the operator? So if I normal order this is a new operator. So what is the operator dual to this in the bulk? This is a double trace operator. Now, if you think of canonical quantizing operators, if you think of the single trace operators corresponding to a field, the double trace operator should correspond, and the field creates a particle. The double trace operator should roughly correspond to like a 2-particle state or something. Multi-trace should correspond to multi-particle state. So it can't be a new operator in the spectrum, or rather, it is a double trace operator, but it can't have a new field in the bulk because it's tied to the previous field.
Right.
Okay. Now, in this window where you're allowed to use the Neumann boundary condition, you're also allowed to use mixed boundary conditions.
Right.
Okay. So if you want to turn on O squared, you want to correlate the source, the A and the B in my notation. Both are normalizable. And you can try to give me B as a functional of A.
Right.
So it could be as simple as a Robin boundary condition where you say it's some linear combination of Neumann plus Dirichlet, or something more complicated where B is some non-trivial functional of it.
Right.
And those would correspond to turning on things of this kind.
Okay.
So double traces are literally effectively trying to do some kind of mixed boundary condition, multi-traces.
Okay.
But they're again most interesting in the regime where the operator stays the single trace operator stays relevant. And you can construct non-trivial solutions with them, which people have explored in various contexts.
Mm-hmm. Thank you.
Okay, so maybe it's a good time to stop the recording and